So in our previous video tutorial, we learned about factor theorem. Now these two theorems, integral root theorem and rational root theorem, are related to factor theorem. Okay. Now before discussing these two theorems, one important thing for grade 9 students of CBSE board. Such problems like these three problems I have taken from your NCERT book. Now these three problems, the way they have been solved in your book, in my opinion, that's not a very good way to explain. It's very confusing because these three problems are actually related to integral root theorem and rational root theorem. Now these two theorems are, I don't know whether it's allowed to use in your examination or not, in maths exam or not. So first check with your teacher whether you can use this theorem or not, and then only use this theorem when you're writing your exam. Okay, now let's begin our discussion. Now integral root theorem and rational root theorem, both these two theorems are actually related to each other, and I'll explain you these two theorems and the algorithm to find the factors of a polynomial. But if I try to explain you this theorem and then this algorithm like by reading, it will literally scare you. Okay, I'll take an example, in fact two examples, and then I'll explain you step by step each and everything. Okay, let's begin. Fx is a polynomial that is equal to 2x cubed minus 3x squared plus minus 17x plus 30. You have to factorize it. Okay, you have to factorize it. Now you cannot apply the splitting of middle term here. You cannot use it. Okay, so what can we do? You have to use factor theorem. That's important. You have to use factor theorem. Using factor theorem. Okay, so if this is the condition that you have to use the factor theorem, in that case what you have to do is you have to use this rational root theorem that says fx is equal to, you know that it's a representation of a polynomial of nth degree, be a polynomial with integer coefficients, So in this case we have 2, we have minus 3, we have minus 17, we have 30. All these are integer coefficients. Okay, then and b by c be a rational fraction in lowest terms, then b by c is a root of fx if b is a factor of constant term a0 and c is a factor of an. Now let me explain you. Take a rational b by c. Okay, now the condition of b by c is that the highest common factor should be 1. Okay, that's the condition. That's what we mean by in lowest terms. Okay, now what you have to do is draw a line like this. I mean, it's in order to explain you, take line like this. When we are talking about b, go to this a0, right? This is a0. Why? Because we know that to represent a polynomial of the nth degree, we write in the last we have a0 and before that we have a1x, so on and so forth. We know all these things. So this is basically what a0 is what? 30. That is a constant term. Write all the factors of 30. So let's write plus minus 1. Why? Because 1 is a factor of every number. So minus 1 will also be factor of this number, because in that case your quotient will be minus 30. When you divide this number 30 by plus 1, your quotient is 30. When you divide this number 30 by minus 1, your quotient is minus 30. That's why it's also a factor. In the same way, you have plus minus 2. When you divide by plus 2, your quotient is 15. When you divide minus 2, your quotient is minus 15. Right? So this is also a factor. Okay, plus minus 2, then plus minus 3, then plus minus 5, then plus minus 6, then plus minus 10, then plus minus 15, and plus minus 30. Right? These are the factors of this constant term 30, and b actually deals with these factors of constant terms. Okay, Now C deals with the factors of this an. Remember, our polynomial is of the form anx raised to power of n, then an minus 1 x raised to power of n minus 1, right? Okay, so our C deals with this numerical coefficient, that is 2, deals with the factor of this one. So what are all the factors here? Plus, minus 1 and plus, minus 2. Okay, now we have explained you that B deals with the factors of this constant term, that is A0. In this case we have 30. C deals with the factors of this numerical coefficient, that is an. That is, in this case it is plus minus 1 and plus minus 2. Now we have to form all the possible B by C which can be roots. It's not necessary that are roots or 0 of this polynomial. They can be, and we have to check that. Possible. Okay, so possible roots or zeros of fx in this case. So now learn how to make it. First take this plus minus 1, right? Divide this with plus minus 1. You will get plus minus 1. Okay, comma. Take this plus minus 2. Divide this with plus minus 1. You will again get plus minus 2. In the same way, take plus minus 3. Divide this by plus minus 1. You will get plus minus 3. So then you have plus minus 5, plus minus 6, plus minus 10, plus minus 15, and then plus minus 30. Okay, so we are done with plus minus 1. Now it's time for plus minus 2. Take plus minus 1, divide this by plus minus 2. So when you divide plus minus 1 by plus minus 2, this B by C will be plus minus 1 by 2. Okay, now take this plus minus 2 and divide this by plus minus 2. In that case you will get plus minus 1. Now we already have plus minus 1 here, so ignore it. Now take plus minus 3 and divide this by plus minus 2. So this B by C fraction will be plus minus 3 by 2. Take plus minus 5, divide by plus minus 2, you will get plus minus 5 by 2. Take plus minus 6, divide by plus minus 2, you will get plus minus 3. We already have plus minus 3, so ignore it. Take plus minus 2, divide by plus minus 2, you will get plus minus 5. We already have plus minus 5, ignore it. Plus minus 15 divided by plus minus 2, you will get plus minus 15 by 2. Okay, now take plus minus 30 and divide by plus minus 2, you will get plus minus 15. We already have here, so ignore it. So we are done with this one also. Now these are the possible roots of fx. These are the possible, not necessary, and we'll have to check it. Okay, now one important thing. We said that B by C has to be in its lowest term, right? Okay, that means that the highest common factor of B and C should be 1. Now if you check these 1, 2, 3 and 4, 1 by 2, 3 by 2, 5 by 2, 15 by 2, these are actually in lowest terms. That's what it's in the B by C form. Okay, now this integral root theorem will be applicable when it's very similar to rational root theorem. It will be applicable when your an, like in this case you have 2, but imagine if it were not 2 here, it was simply something like this, right? It was something like this. Here you have an is actually equal to what? An is actually equal to 1. Okay, if an is equal to 1, then tell me, when you deal with this B by C, now B deals with the factors of 30, so you'll write all these factors. Okay, C deals with this an. In this case it is actually 1. So what will be the factors of 1? The factors of 1 will be plus minus 1, right? So when you divide this plus minus 1, like in this case you have plus minus 1 here, So 1 plus minus 1 divided by all these, if you look at all these factors, like in this example, you're only going to get these integer form of possible roots, right? No other fractional roots, that is rational roots. No fraction roots or rational roots, right? Only these integer roots. That is what this integral root theorem says. If your an is equal to 1, that is leading coefficient. Leading coefficient means an. If your leading coefficient is 1, there you are actually dealing with integral root theorem. And what we mean by that is that in that case you will only have these possible integer roots of fx, and then whatever step you will take will be according to this rational root theorem only. That is in this case these algorithms. Okay, only difference is that your an is equal to 1, then it's time to think of integral root theorem, but algorithm is going to be the same. Okay, this thing is clear. Now let's write 2 here. Let's remove it. Now your fx is 2x cubed minus 3x squared minus 17x plus 30. Now here is a little time taking job. You'll have to check these different possible roots by putting here, like if first you put f1, then put f minus 1, then you'll put f2, and so on and so forth. The point is you have to check all these possible roots by putting here at the place of x, and whenever your fx becomes equal to 0, it means that that's actually the root. That is actually the root. Now to save our time, I have already checked it, like it's given in the book, to be honest. So f2, when you put f2, you will get 0. Like you can check here, if you put 2 here at the place of x, your final polynomial will be 0. It means that now here you have to remember your factor theorem. Your factor theorem says that if f a is equal to 0 for an a where a is any real number, then your x minus a is a factor of fx. So by that x minus 2 is one factor of this fx. Okay, since it is a cubic polynomial, whose cubic polynomial means that the degree of the polynomial is 3, it will have 3 linear polynomial factors. It will have 3 factors that are linear polynomials. So one is x minus 2. The next you check for f minus 3. When you put minus 3 here, you'll get 0. Okay, it means that if f minus 3 is equal to 0, it means that x minus 3 will be a factor, that is x plus 3. Remember the factor theorem, if f a is equal to 0, then x minus a is a factor of fx. In this case we have actually f minus a because it is minus 3. That means x minus a, at the place of a it's x minus a. That's why it becomes x plus a, right? Okay, now we have x plus 3 as our next factor. So x plus 3 is our next factor, and then f5 by 2 will give you 0. So your next factor will be x minus 5 by 2, right? So x minus 2, x plus 3, and x minus 5 by 2. These are the 3 factors we have got. Okay, so let's go to this algorithm part. Here, if you see here, we have obtained the polynomials. Let the polynomial be like this. Now find all possible integer and rational roots in lowest terms of fx by using integral root theorem and rational root theorem. That's what we discussed. And let the roots be alpha 1, alpha 2, alpha 3, and alpha k. Okay, now in this case actually it's saying that we have our 2 roots that are 2 minus 3 and 5 by 2. These are the 2 roots. Now it's saying that if the number of integer and rational roots is equal to the degree of the polynomial fx, that is k is equal to n. Now what's k and n? Here when it's saying that actually when your possible roots are alpha 1 alpha, sorry, when your roots are that you have tested alpha 1 alpha 2 alpha 3 and so on alpha k, right? Alpha k. If your k is equal to n, if your k is equal to n, it means that it's alpha 1 alpha 2 and so on and alpha n. It means that you have now n roots. Like in this example we have 3 roots, and which is equal to the degree of this polynomial, that is 3. In that case, write fx is equal to lambda. Pay attention to this. It's lambda, it's alpha 1 alpha 2 alpha 3 alpha k. When alpha k is equal to n, that is you have exactly n roots, then write fx is equal to lambda x minus alpha 1. Why? If alpha 1 is a root, x minus alpha 1 is a factor. If alpha 2 is a root, x minus alpha 2 is a factor, and so on and so forth up to x minus alpha n, right? That's what we mentioned here. If 2 is a root, x minus 2 is a factor. If minus 3 is a root, x plus 3 is a factor. If 5 by 2 is a root, x minus 5 by 2 is a factor. Then write fx is equal to lambda, and then you have to find out the value of lambda. That's explained here, and I'll explain you how to do that. So write fx is equal to lambda, or let's write the fx here. So in this case our fx is, let's copy this, Control C, Control V, is equal to lambda, and then you have x minus 2, you have x plus 3, and then you have x minus 5 by 2, right? We have this. Now it's saying that now replace x by any value different from alpha 1 alpha 2 alpha n. What it's saying that you have these 3 roots, 2 minus 3 and 5 by 2. Put any value at the place of x other than 2 minus 3 and 5 by 2, so that we can calculate this value of lambda. Okay, simple. Put 0. It's saying you can put any number, simply put 0. That will make our calculation simpler. So if you put 0 here, you'll get 2 multiplied by 0, 0, 3 multiplied by 0, 0, 17 multiplied by 0, it was 0. So on the left hand side you have 30, then this is lambda. Put 0 here, you have 0 minus 2 is minus 2, 0 here is 3, 0 here is minus 5 by 2. So this gives you minus 5 by 2. Okay, so this is basically what? Minus 2 multiplied by 3 multiplied by minus 5 by 2. This can be written as, this is minus 2, so minus 2 multiplied by minus 5 by 2 multiplied by 3. This 2 gets cancelled. You have minus 1 actually here now. Minus 1 multiplied by minus 5 is what? 5. Multiplied by 3 is what? 15. So from here you get 30 is equal to lambda 15. Then lambda is equal to then therefore 2. Lambda multiplied by 15 is equal to 30, therefore lambda is equal to 2. So if your lambda is equal to 2, so you have to simply write it like, I'm going to replace it here, replace lambda by 2. So you write 2 here, right? If you write 2 here, now it's the required, let me remove this. This is your required factorization of this polynomial 2x cubed minus 3x squared minus 17x plus 30. We can do one thing here, like this is one step we can add here. This is actually 2. So if we write this as, if we take LCM here and if we write it as if we write it as 2x minus 5 by 2, we can write, right? And then we can actually cancel this. 2 divided by 2 will be 1. So let's remove it. So now basically this is your factorization of this polynomial 2x cubed minus 3x squared as 2x cubed minus 3x squared minus 17x plus 30 is equal to x minus 2 multiplied by x plus 3 multiplied by 2x minus 5. This is the factorization of this polynomial. Okay, so the only difference, the only time when you will use the integral root theorem is that when your this leading coefficient is 1. Rest all the thing will be same. Okay, last important thing and very important thing. This algorithm, point number 4, and I'll explain you with an example here. I have already written it here so that we can save our time. Fx is equal to 2x raised to power of 4, and then we have some terms here. Okay, the point is that it's a biquadratic polynomial, that it is x raised to power of 4. Sometimes what happens when we calculate the possible rational roots, like in this case we have calculated the possible rational roots in the same way you will do it, that is b by c. Your b deals with all the factors of 6. So in this case you have plus minus 1, plus minus 2, plus minus 3 and plus minus 6, right? Your, in this case, constant is minus 6. Your constant is minus 6. Remember, we always take the negative sign. And then if when c deals with this 2 here, so in this case 2, the factors will be plus minus 1 and plus minus 2. And when you will try to find out b by c, as we did here, you will get these possible roots. Now these are actually possible roots, not exactly, these are not exactly the roots. So in this case, again, when you check for f minus 1, you will get 0, and when you will check f minus 2, you will get 0. F minus 1, f minus 2, only 2 factors obtained. When we try to find out the factors in this roots in this case, the number of roots were exactly equal to the degree of this polynomial. But in this case now, we can out of these possible roots, we have only minus 1 and minus 2 that are the factors we can obtain from these possible roots. So what to do? It's a biquadratic polynomial, that is its degree is 4. It should have 4 factors. It should have 4 roots, and from that roots we can write down the possible factors. So what to do? In that case, what we do is, that's explained here. If the number of integer and rational roots is less than the degree of the polynomial, then divide fx by x minus alpha 1, x multiplied by x minus alpha 2, and so on, and obtain the quotient qx. Okay, so let me explain you what we are actually doing here. So only 2 roots we can obtain, but we need 2 more, because since it's a biquadratic polynomial. Take this fx, this fx is what? Our fx is 2x raised to power 4 plus x cubed, and so on, we have written here. Now if minus 1 is a root, so x plus 1 is a factor by the factor theorem. If minus 2 is a root, x plus 2 is a factor by factor theorem. That is, you have to multiply this. Now when you divide this, this is the quotient. This is the quotient you get after dividing it. That's what it's talking about. That here, this point number 4, obtain the quotient qx. Obtain the quotient qx. This is what it's saying, obtain the quotient qx. So we have obtained the quotient qx, this is qx. Then what's written here, I'm not going to read that, otherwise it will take time, I'll explain you. Then you take this qx, write this fx is equal to lambda, as we did in this example. Lambda multiplied by x plus 1, because x plus 1 is a factor, x plus multiplied by x plus 2, because x plus 2 is a factor, multiplied by this qx, that is 2x squared minus 5x minus 3. Okay, now what you have to do is calculate this value of lambda as we did in this case. Same thing, put some value here, like in this case you put x equal to 0 on both the sides, you get lambda is equal to 1. Now since you get lambda is equal to 1, we write it like this: lambda is 1, so then it's here only x plus 1 multiplied by x plus 2, and this 2x squared minus 5x minus 3. Now it's a quadratic polynomial, right? It's a quadratic polynomial. And if you pay attention to this minus 5x, the concept of splitting of middle terms, so this is 2x squared minus 5x minus 3. We know the concept of splitting the middle term, so this is 2x squared minus 6x plus x. So minus 6x plus x will give you minus 5x, and minus 6 multiplied by 1 is what? Minus 6. That is equal to 2 multiplied by minus 3, right? The splitting of middle term. So we use in the when we calculate the factors. So from here you get, finally you'll get 2x plus 1 multiplied by x minus 3. That is, solving this will give you 2x plus 1 multiplied by x minus 3. Finally you write these two factors, that is x plus 1 multiplied by x plus 2 here, and this is multiplied by, we have simply simplified this quadratic polynomial. So this is your factorization of this polynomial. These two factors, that is x plus 1 and x plus 2, we obtained from the factor theorem, and the rest two factors, that is 2x plus 1 multiplied by x minus 3, we obtained from by splitting the middle term of this quadratic polynomial. So the point was that sometimes your number of roots that you can obtain are exactly equal to the degree of the polynomial. In that case you will use this step 3. Otherwise, when your number of roots that you have obtained from factor theorem, from these root theorem, if they are less than the degree of polynomial, then you use this fourth step that we have discussed here, and on the basis of that you calculate the factorization of this polynomial. So this was all about integral root theorem and rational root theorem, and I hope that I didn't confuse you. I tried my best to explain you, right? And so yeah, and CBSE board grade 9 students, please ask your teacher before using this theorem. I don't know whether it's allowed to use in the exam or not, but the way they have explained these such problems in your book, in my opinion, that's not a very good way to explain. It's quite confusing.